Hello students. In a previous lecture, we have studied about the equivalent circuit of an induction machine when the rotor was stationary. We've seen various how the equivalent circuit is being formed. Now in today's lecture, we are basically will study the equivalent circuit when the rotor starts rotating at some slips, let's say s. So this was your equivalent circuit when the rotor was stationary. This is what we have developed in your previous lecture. You can see that the slip is equal to 1. This is very important. Now in today's lecture, we'll see what will happen to the equivalent circuit when the rotor starts rotating at some slip s. Now as we all know that the stator structure will remain as it is, as was previous this thing. This will remain as it is since this frequency of the stator is always the supply frequency. But the rotor structure will obviously change. Why? Because it depends on the frequency. As soon as the frequency changes, as soon as the rotor starts rotating, slip comes into the action, and then frequency of the rotor changes, and hence induced EMF changes. This standstill reactance changes, and the value of current also changes accordingly. Now we'll study about this structure. Now this is the structure as soon as the rotor starts rotating. Now we need to join the stator structure and the rotor structure. We need to refer all these rotor parameter to the stator parameter exactly the same way as we have done previously when the rotor was stationary. Okay. Previously it was easy to join the stator structure and the rotor structure because it was exactly the same case as we have studied in our transformer. Why? Because when the rotor was stationary, the supply frequency, the frequency of the stator body means the primary side, and the frequency of the rotor body means the secondary side was same. Why the frequency was same? Because this rotor was stationary, slip was equals to 1. So rotor frequency was also supply frequency. So when the frequency was same, then you can see the E1 and E2 ratio was constant. So whenever this E1 and E2 ratio is constant, then only you can join the primary and secondary sides. Now in this structure, what is the issue? The issue is that now the ratio of E1 and E2 is no longer constant. Why? Because E1 divided by E2, E1 divided by S times E2, we'll get S times E2 has changed to slip times E2. Now this slip is continuously changing, and when this slip is continuously changing, then this ratio will never become constant. Okay, so we cannot join this primary circuit and secondary circuit as we were doing when we have studied our transformer. Okay, so this is the main issue. So what are we doing is that now for this circuit we'll calculate the value of the current. Now the value of the current is this thing. I2 is equal to nothing but SE2 divided by root of R2 square plus S square X2 square. You can easily find out the current in this circuit. This is the voltage and this is the impedance. You can find out the value of the current. Also, if you take S square common, then we'll get this expression. Now this expression, this circuit for this expression can be represented by this thing, this circuit. E2 is the voltage, R2 by S is the resistance, and X2 is your reactance. Okay, so what are we going to this why basically I'm doing this thing is that you can see that the value of the current in this circuit and in this circuit is same. Value of the current in this circuit and in this circuit is exactly the same. Okay, also you can see basically why we are shifting from this circuit to this circuit. This circuit is basically called an imagined circuit, because we know that actual circuit is this thing, that with the slip E2 is also varying, with the slip this X2 is also varying. So actual circuit is this thing, but this circuit we have imagined just for calculation point of view. And one more thing which is very modern, which I'll tell you why we are shifting from this circuit to this circuit, because we need to we need to refer our rotor side to the stator side, and I've already told you for referring the rotor side to stator side, the ratio of E1 and E2 should be constant. Then only we can connect these two circuits. So now when we have changed this circuit to this circuit, now E2 is constant. E2 is no longer a function of slip. Okay, so now you can connect these circuits. See, these things, this is what thing I'm doing now, these are only for the point of calculation point of view, for making the circuit exactly, but the actual circuit is this thing. But we'll see that there is no difference in this circuit and this circuit. Why? Because one thing we have already seen, that the current in this circuit and this circuit is exactly the same. But the current in this circuit is given by this thing, and the current in this circuit will be given by this thing, and we know that this is equal to this. Both these terms are equal. So that means the current in this circuit and in this circuit is same. Another factor what we need to see is that whether the power factor of this circuit is equal to this circuit. Because if these circuits are equivalent, if they are same, then obviously the power factor of this circuit should also be equal to the power factor of this circuit. Okay, because the see the stator, what is the stator sees? Now stator sees what is the current flowing in the rotor. So if it is same in both the circuit, stator would not know whether the circuit is like this or this. It will see three things: whether the current in the rotor is same or not in both these circuits, whether the power factor of both these circuit is same or not, and whether the real power consumed by this circuit and this circuit is same or not. If all these three parameters are same in these three, both these circuits, then we can obviously replace this circuit by this circuit. Okay, and the stator could not identify which circuit is being put over here, because for stator it only needs three parameters: that what is the current flowing in the rotor circuit, what is the power factor of the rotor circuit, and what is the real power consumed in the rotor circuit. So these three parameters must be same. Now what are we going to do is that I'll show, as I've already shown, one parameter is confirmed, that I2 in this circuit and in this circuit is exactly the same. Now we'll talk about the this thing, your power factor. All these things are nothing but you can all take a quick um, reading. You can do a quick reading of these things. We've already discussed about these things. What does these things say is that whenever an I2 current starts flowing in the rotor circuit, this is the rotor circuit, where as soon as this current I2 starts flowing in the rotor circuit, an RMF will be, as I've already told you, an RMF, as soon as the current starts flowing in the rotor winding, the three-phase windings are so placed that an RMF will, this since this current produced will be again three-phase balanced current, and this rotor winding again three-phase balanced winding, 120-degree displaced, spatially displaced. So an RMF of this rotor will be induced, and that RMS speed and what will be the speed of the rotor field, and those things we have already discussed. You can go through it again. So these are the same things which have been done. Now we need to see what is the value of the power factor, both the circuits. So the value of the power factor for your previous circuit means for your original circuit, this is the original circuit. Okay, and this is your imagined circuit. Okay, so what will be the power value of power factor for this circuit? Tan inverse of x s times x2 divided by r2. Power factor is this thing, and for this, tan inverse of x2 divided by r2 by s. So this is what they have shown you, that power factor is nothing for both the circuits will be tan inverse of s times x2 divided by r2, and again the x2 divided by, for another circuit, this thing is x2 divided by r2 by s. So you can, s will go upward, so you can see that the power factor of these circuits is also same. So another condition is satisfied. Now we need to see whether, so this is the actual circuit and this is your imagined circuit. Actual circuit is this thing, s e2 s x2 and then r2. Imagined circuit is e2 x2 r2 by s. Okay, now we can see this is written that with respect to the stator, both circuit 1 and circuit 2 are same, and stator component and stator cannot, this is cannot, stator cannot discriminate between actual motor and imagined motor, as power factor in both is same, and current in both is also same, and hence field produced by rotor is also same in both the cases, as B max, that is the field intensity, as B max depends upon I2 max. So if current is same, then field produced will also be obviously same. But what about the real power? So is there a difference between the real power? So we'll see. So see, the real power consumed in this circuit, if we talk about this circuit, so what is the real power consumed in this circuit? The real power will be only consumed by resistance in this circuit. So what will be the value of that real power consumed? If current is I2, then I2 square into R2 is given as the real power consumed by this circuit. Okay, I2 square R2, I square R is the real power consumed. So in this circuit, okay. Now what will be the real power consumed in this circuit? It will be I2 square into R2 by S. Are you getting it? I square R again. So but value of R in this circuit is R2 by S. So real power consumed in circuit 1 is I2 square into R2, and in circuit 2 it is I2 square into R2 by S. Now you can say that no, the real power consumed in both the circuits is different. So how these circuits are equivalent? That means these circuits are not same. So what does this signifies? The real power consumed in circuit 1, that is the original circuit, what does it signifies? It signifies I2 square R2 is nothing but the rotor ohmic loss. This is the rotor resistance R2. So I2 square R2 is nothing but rotor ohmic loss. What is the active power loss in rotor resistance? This signifies only this thing. Now what does this signifies? Before discussing this, we have already studied the effectiveness or the significance of your slip. So I'll again revise quickly. So what does this slip signifies? Slip signifies that whenever there is an opposing torque, whenever there is some opposing, so there is some loss in power, that then slip will be generated. See, when is basically slip generated? Because we know that whenever rotor starts, suppose there is an induction motor which is rotating at 1500 rpm. 1500 rpm, synchronous speed is 1500 rpm. Now suppose the rotor at no load is rotating. No load means there is no load on the induction motor, means induction motor is only rotating the shaft. There is no external load on that shaft. Okay, motor is only rotating that shaft. So if induction motor is running on no load, and if the synchronous speed of the induction motor is 1500 rpm, so you can say that if it is rotating on no load, then the speed of the rotor will be around say 1470 rpm, 1470 rpm. It cannot be equal to 1500 rpm. As we have already discussed, we have discussed that the rotor speed can never be equal to the synchronous speed. Why? Because if it is a practical machine, then there will be some friction of the shaft which the induction motor is rotating. There will be some friction because of that shaft, and hence due to that friction some power, some torque will be lost in providing that friction power. Okay, so that opposing torque, in order to provide that opposing torque, some power will be lost in that, and hence some power will be lost, and hence some speed will be lost in providing that power. Hence due to that friction some speed is lost, and when the speed is lost, then the rotor will obviously can never attain synchronous speed, and it will, the difference between the synchronous speed and the rotor speed is nothing but your slip. So this slip basically signifies that there is some opposing torque. Now what will happen? Suppose that induction motor was running earlier on no load. Now if I put some external load on the shaft, now the motor is rotating the shaft, the weight of the shaft, as well as the external load which I have put on that shaft. Now the slip, rotor speed will further decrease. Why? Because now the induction motor has to provide two powers. Two opposing powers are there. One is due to the friction, and other is due to the load, that is external load that is put on that shaft. So we need to provide these two powers. So even more, the speed of the rotor will fall back even more, and hence the slip will increase even more. Why? Because the slip is nothing but the difference between the synchronous speed and the rotor speed. So rotor speed will decrease, so the difference between the synchronous speed and rotor speed will increase, and hence your slip will increase. Are you getting my point? So this basically slip represents, if there is a slip present in any machine, in an induction machine, if there is a slip, that means that there is some opposing torque. There is some power, some active power is consumed in providing that mechanical torque. That power is given, where does this power goes? This slip power, this basically goes in providing that mechanical power. Suppose if there is if the motor is rotating only shaft, then for rotating that shaft some mechanical power is extracted, and hence this slip is generated. If the motor is rotating shaft plus some external load which is put on that shaft, then the machine is providing mechanical power which is equal to the mechanical power consumed by the shaft plus the mechanical power consumed by that load. So this is the significance of the loop. So now when we talk about this I2 square into R2 by S, then this power, this active power basically consists of two powers. One is the rotor ohmic loss, I2 square into R2. One is the rotor ohmic loss power, active power consumed in the rotor resistance, and another is the active power consumed in the mechanical power. Active power consumed for providing the mechanical, for converting to, is converted to the mechanical energy. It is rotating that shaft and that external load. In this power, in circuit 1, I2 square into R2 is just rotor ohmic loss. Now this circuit 2 power, this is rotor ohmic loss as well as the mechanical power. Okay, so that is why these two powers are not different. Okay, you are getting both these circuits are producing the same active power. That's why we say that the both these circuits are same. Why? Because in this formula, by if we are using this formula, then we are only saying that what is the rotor ohmic loss. I2 square into R2 is just giving the power loss, active power consumed in the rotor resistance. It is not showing the power consumed by active power consumed for mechanical energy. While this power is not only showing the rotor resistance, it is also showing the mechanical power also. In this also, the rotor ohmic loss is again I2 square into R2 only. And this is also rotor ohmic loss is R2 square into R2 only. But the extra power, this is since this circuit 2 power is greater than this 2. Why? Because we know that the value of the slip is always less than 1. So this thing will circuit 2 power will be obviously greater than this. Why? Because why it is greater? Because this is including the rotor power as well as the mechanical power used for rotating the shaft and the load. So that is why we say that both these circuits are exactly the same. Active power consumed is exactly the same. Only thing is that in this thing we have not included the active power consumed, mechanical power, active power consumed in rotating the shaft. We have not calculated this thing. How do we calculate these things? We'll further study. We'll study in your next lectures that how do we calculate the mechanical power consumed. Now this power consists of both the rotor ohmic loss, power consumed in rotor resistance, as well as the power consumed in mechanical loss. This is very important point, and you should be very clear about these things. Hence, this is the complete explanation. You can see now. Suppose if we subtract this power I2 square into R2 from this power, what are we going to get? As you can see that this power is nothing but mechanical power plus active power consumed in rotor resistance, and this is active power consumed in rotor resistance. So if we subtract this power from this power, you will get what? This is mechanical plus rotor resistance power minus rotor resistance power will give you mechanical power. So this power minus this power will give you mechanical power, which I have written this power minus this power is mechanical power consumed by opposing torque. This is opposing torque that is provided by shaft, or if say some external load is provided on the shaft, then shaft plus that load. So basically both these machines are one and the same thing. Now we'll study the equivalent circuit referred to stator of three-phase induction motor. Now we can join these circuits like this thing. Why we can join these circuits? Because now we know that we have replaced, we cannot join these two circuits. Why? Because the E1 divided by E2 in these two circuits is not constant, since E2 is a function of S. So we have replaced this circuit by this circuit, imagine circuit. In this circuit, E2 is constant, X2 is constant, only R2 is changed. So E1 divided by E2 is a constant, and when E1 divided by E2 is a constant, then you can connect those circuits and see when we are connecting, this stator structure is remaining same. E1 divided by E2 is constant, and you can see this X2 is no longer S times X2. Why? Because in an imagined circuit, what were the things in imagined circuits? It was E2, X2 and R2 by S. So we are multiplying A square into X2 and A square into R2 by S. So this is how we are joining these two circuits. This is basically your imagined circuit. Now this power basically consists of both mechanical power as well as the power loss and active power lost in rotor resistance. This is how why we have discussed all those things, because for joining these stator sides and rotor side circuits, you need to have a constant value of E1 divided by E2, and hence we have considered this rotor, this imagined circuit, and so that we can join these circuits. Now we have joined these circuits, and the things as this thing is very important, that this value of the xm is very greater than R1, X1, R2 and X2, because R1, X1, this is stator winding resistance, take a leakage where reactance, this is rotor winding resistance and rotor leakage reactance. So these values are very small. Okay, so you need to be very careful about these things. So yeah, we'll be discussing further on this topic in your next lecture. So this is all for today. Kindly go through the previous lectures also. Thank you very much.